Okay, ladies and gentlemen, welcome to our first online lecture of the semester. So today we're going to go ahead and focus on chapter 1 in our textbooks. And admittedly, before we get started, I just kind of want to do a quick overview about the objectives, kind of the big goals, the big picture, if you will, of our course. And specifically, what we're going to say about our course objectives is that we're going to be kind of really developing our critical thinking skills. Now, there's more we're going to do to this class beyond that, of course. But as a big picture, we're going to be developing critical thinking skills because it turns out that that's necessary for any type of science, astronomy included as well. We're also going to be understanding elementary, which is basically a phrase for introductory, astronomical and physical terminology and processes. Now, first things first, this class is Astronomy 20, but you'll notice that in the parentheses I say and physical. The reason why is that for the first 2 to 3 chapters of our textbook, it's almost indistinguishable between this class of astronomy and physics, accordingly, physics 20. So there's overlapping ideas, there's overlapping terminology, there's overlapping processes that occur in the first 3 chapters of this textbook with physics and astronomy. So that's why I have the parentheses there. This isn't a physics class, but the ideas that we're going to be using in those chapters are the exact same ones that are used in physics for its first 3 chapters as well. Now, admittedly, things that we're not going to be focusing on in this class. This class is titled Astronomy with an N, not Astrology with an L. So we are not going to study astrology. So unfortunately, if you were looking for your horoscope in this class, you're going to have to look somewhere else. We're also not going to be performing difficult numerical calculations. Now, there's a little subtlety in that statement. So basically for this class, you need to know how to add numbers together, like 10 and 15. You need to know how to subtract 2 numbers like 55 and 13. And you also kind of need to know how to multiply and divide numbers from each other, like 1,000 divided by 10, or maybe 12 multiplied by 5. If you can do that basic arithmetic, then you're okay for this class. It's really not going to be too challenging beyond that. But we're not going to be doing hardcore, kind of where you need to know order of operations, or you have to use advanced math like calculus to do well in this class. That's not the goal. But this class does involve numbers, not too many numbers, but enough to where they're going to pop up every lecture essentially. But you do have to kind of be able to handle some basic arithmetic. But we're not going to be doing any of the hardcore stuff. You might be doing that, emphasis on the word might, but you might be doing that if you take Astronomy 25, depending upon who your instructor is. But for this class, don't worry. Numbers will pop up from time to time, but they're not going to be very hard numbers to deal with. And plus, when we take our exams online, you're going to have access to a calculator while you take the actual test. It's going to be kind of on the lower right-hand side, I believe, of the screen. And you can just click the button, access the calculator, and boom, there you go. So it won't be a problem if you need a calculator. But nonetheless, we're focusing on the top 2 ideas, this idea of terminology, aka vocabulary, and processes, kind of way things work. We're not going to be focusing on the bottom 2 for this class. But with that kind of being said, we need to understand basic astronomical terminology, aka vocabulary. So we're going to go ahead and actually start one step further behind. So what do I mean by that? Well, it turns out that astronomy is one of many sciences. So to understand astronomy, we kind of need to understand the basic terminology of science as well. And what we're going to say is that our first terminology, our first vocabulary in chapter 1 is going to be called a fact. And just like you see here on the right-hand side of the screen, a fact is defined as an agreement between 2 or more observers about the same phenomenon. So for example, when you're looking at this picture that I have right here, what color does the water look to you? Okay, well, when I look at it, it looks blue. So if you and me both agree that the water looks blue, then that's a fact. Now, in everyday conversation, the word fact has a really kind of sinister undertone in the sense that some people, erroneously, but some people think that a fact is an immutable, truth, aka facts can never change. But we're going to find out that's actually not true. Facts are not objective truths. Facts are just agreements. That's all that they are. And sometimes people agree about things and then later change their mind or find out that they're wrong. So facts are fluid depending upon what the phenomenon is and how we observe them in the first place. But nonetheless, the water looks blue to both of us. A follow-up question, a different phenomenon about the same picture that I can ask you is, if you look at this piece of land right here, what shape does it look like to you? Well, to me, it looks flat, and the ocean looks flat. So if you agree with me, then we can say that in this picture, the earth looks flat and the ocean looks flat. That's just an agreement that we have based upon using our eyes to make an observation about the shape of the land and the water. Okay, so there's more facts. And we can also talk about facts involving the clouds in the atmosphere and so on and so on. And there's a boat in the picture and more facts. Okay, but again, facts are just agreements. But it's what we can do with facts that makes them interesting. So for example, what we're going to say is that a hypothesis, sometimes called a model, but admittedly, a model is usually very mathematical in nature, whereas a hypothesis can be mathematical, but it's not required to be mathematical. But our book kind of uses the two interchangeably, which I kind of frown upon, but I'll just go ahead and kind of nod my head, shrug my shoulders, and move on with it. But a hypothesis or a model is basically an educated guess. However, when we say the phrase educated, that means that it's based upon facts. So another way to think about this is that a hypothesis is a guess based upon facts. So for example, if you think back to this previous picture that I have right here, it was a fact between you and I that the ocean looks flat and the land in the distant part of this picture also looks flat. So that's our fact. And what I'm going to say is that based upon that fact, I'm going to make the guess that the earth is flat. So I don't care about whether it's correct or not. That's a different part of this whole terminology. But the guess that I'm making based upon the facts is that the earth is flat, kind of like this painting that you see right here of the ship approaching the edge of the earth. All right, well, I've made a guess based upon facts, but is that guess correct or is that guess incorrect? Well, it turns out that if your hypothesis is objectively tested, aka well tested, as we call it, and that hypothesis has not been disproved, aka not proven false, then that hypothesis graduates. It turns into, it evolves, I guess if you wanted to say to be dramatic, what we call a scientific law, or as our book just says, a law. So a law is just a well-tested hypothesis that's still correct. Now this picture that you see right here, it's an old picture from the early 2000s, I forget the exact year, but it's a picture taken from the International Space Station, which is at a very, 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 very high altitude above the Earth's surface. And based upon this picture that we're seeing, the test, if you will, is my hypothesis from the previous picture correct about the Earth? Does the Earth look flat in this picture? Absolutely not. We can clearly see that the Earth is curved from this very, 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 very high altitude point of view. So my hypothesis about the Earth being flat has been proven incorrect. It's wrong. So therefore, my hypothesis can't be considered a law because it's been disproved. End of story. Well, it turns out that there are many hypotheses that can be made about a phenomenon, and they tend to be related to each other. That's never a guarantee, but they usually are related to each other in some manner, in some way. And when we recognize that relationship between laws that are really just describing the same phenomenon, just from different points of view, we can lump them together to form something called a theory. So as it says here, theory is a group of information that has proven hypotheses. Well, proven hypotheses are really just laws. So basically a theory is a bunch of laws that are really just talking about the same general thing. Okay. Now, there are going to be many theories that we're going to talk about throughout the course of this semester. The biggest one is the theory of relativity, but that's not the only one. There's lots of others that are going to pop up as well. But it turns out that theories tend to be very generic. Laws are more specific in behavior, in description of the phenomenon. But it turns out that most theories are very difficult to explain. So what we do is we introduce this vocabulary called concept. And concept is the framework of a theory. So for example, there are several concepts that we're going to talk about throughout the semester to explain some very high-level theories that we're going to talk about. For example, the idea of energy, when we get to chapters 3 and 4, is a concept that we're going to be used when talking about the theory of electromagnetic radiation. In a similar sense, when talking about the theory of motion, we're going to introduce the concept of time. I know it's kind of weird to think about time as a concept, not a separate variable or a fact, but time was introduced to explain the theory of motion. So there's other concepts that are out there as well, and we'll encounter them when we get to them in future chapters. But a concept helps to understand and explain a theory. A theory gives us a generic description of a phenomenon. Laws are very specific, and those laws are based upon hypotheses, which themselves are based upon facts as well. So all 5 of these vocabulary terms are kind of interrelated with each other. They're kind of glued together in a very interesting type of way. And that interesting type of way is something called the scientific method. And the scientific method is a process that scientists, including astronomers, use to help the body of knowledge, to help the field of knowledge, to help astronomy, in our case, grow, evolve over time. And just like you see in this flow diagram, it's very complicated, but it does kind of relate to the definitions of these words that we talked about in the previous slide. So for example, the first thing you've got to do, like I showed you in that picture of the water, is you have to make an observation. The water looks blue, it looks flat, there's clouds above it, et cetera, et cetera. You have to make an observation. And then based upon that observation, just like you see right here, then go ahead and create a hypothesis to explain, to justify those observations. All right. And then go ahead and test that hypothesis. In reality, if you test a hypothesis and it passes, you should really test it a few more times. Because if it passes one time, there could have been a mistake in the measurement. There could be a little bit of bias or favoritism. So it's always good to check things multiple times just to make sure that you really got it right the first and the second time. But what's unique about the scientific method is that if you test a hypothesis and it fails, you basically have to go back to the drawing board. You have to go back to the hypothesis or to the facts that led to the hypothesis. One of them is wrong, or maybe both of them are wrong. But you can't keep moving forward if your hypothesis fails. If you are wrong, that's it. It's over. You have to basically start over. You can't just keep pushing it forward because the scientific community will not accept that. But if your hypothesis passes rigorous testing many times, then just like you see right here, it'll graduate. It'll turn into a law. And again, just to be thorough, a little paranoid, but thorough is a better way to think about it. It's always good to test a law, just to make sure that, again, the hypothesis was correct in the first place. If while testing the law, you fail, the experiment fails, you have to go back to the drawing board. It sucks, but this is a way for us to make sure that what's coming through the process is truthful, is an accurate description of the universe around us. And the very last part down here is that if you have multiple laws, S meaning plural, many of them, and they all connect together to describe one underlying phenomenon, and they're true, they're not incorrect by that association, then we have a theory. But again, if you test the theory and it fails, just like you see with this green blurb right here, you've got to go all the way back to the drawing board. So being a scientist, especially when dealing with research in science, it can be a tedious process because there's lots of checks along the way. But you can think about this as kind of like food. You would want people to check the food that you eat before you eat it. You wouldn't want to kind of just trust somebody's word. You would like to have some sort of actual documented evidence that the food you're eating is safe, it's healthy, it's true in effect. And we as scientists kind of believe the same thing. if there's an idea that we're going to put forth and accept, we want to make sure that it's truthful to the best of our knowledge. So that's why this process is kind of so long and so detailed, because usually what comes out of it is truth. Now, there have been cases where theories have been disproved over time. We have better equipment, we have better knowledge, we just kind of grow as a species. And then when we retest the theory, we find out, oh crap, you know what? We got the original test wrong. That theory has to be discarded. It doesn't happen often, but you can do an easy kind of Google search to figure out theories that are no longer valid due to increases in technology and better testing methods. But that's good, because even though the theory lasted as long as it did and it failed, that means that we're not accepting a false statement. We're not accepting a false truth about some behavior. We're back to the drawing board, but now we're moving in the right direction. We're going to get closer to the actual truth in that case. So we'll talk about one such theory in a future chapter, but I don't want to kind of spoil the surprise just yet. So let's go ahead and kind of take a look at an application of this scientific method. So this statement that you see right here, have you heard this statement before? Someone kind of saying in a casual, everyday conversation, usually in the context of an argument, but just in casual, everyday conversation. That's not a fact. It's just a theory. They usually say it in a dismissive kind of tone or in a dismissive type of manner, like what you've said is not true because it's just a theory. Okay. So is this a correct statement based upon the scientific method and the vocabulary that we've learned? No, this statement is incorrect. However, can the statement be improved? To kind of quote from Bob the Builder, the animated character from the TV shows, can we fix it? Yes, we can. Now, there are many ways that we could fix this statement. I'm going to go ahead and fix it as easy as possible. But before I do that, let's just go back to the flow chart. So here is that same scientific method flow chart. And the statement referenced two vocabulary terms, a fact and a theory. So facts are here near the very top of the process, the very kind of inception point of the process. Theories, though, they're down here. Basically, they're at the bottom of this process. And what I want you to notice is that theories have undergone rigorous testing. They might still be wrong, but they have undergone rigorous testing. A fact, on the other hand, just like we said, is an agreement between two or more observers. Hopefully they know what they're looking at, they're competent, but two or more observers. There's been no testing. It's just an agreement, a handshake, if you will. So based upon that identification, the easiest way to fix this statement is just to switch two words. Can you take a guess as to which two words? Theory and fact. The better way to say what you're trying to convey is by saying, that's not a theory, that's just a fact. Because basically what you're telling the person is, what you've told me has not been tested, it's just an agreement that you had with somebody else. So theories, well tested. Facts, no testing. And it's important that you, as an everyday citizen of the US, enlighten people when they make a mistake. So you don't have to insert yourself into somebody else's conversation, but it might kind of be helpful for you to correct somebody when you hear them make the incorrect statement that I have in quotations at the top, and just kind of politely say, well, I think what you meant to say is that's not a theory, it's just a fact. You're welcome for the free advice. Have a nice day. Continue with the argument. But still, for our class, it's important to understand the difference between these two words and why that statement above, that everyday statement, is in fact incorrect. All right, so we understand the basic ideas of vocabulary and the first process of science, aka astronomy as well. But it turns out that there are many different types of hypotheses that can be created. So for example, the two types that pop up in my head immediately are philosophical hypotheses, because they're part of philosophy, and then scientific hypotheses, because they're part of science. Well, this isn't a philosophy class, so therefore we really don't care about philosophical hypotheses. We want to focus instead on scientific hypotheses. So in order for a hypothesis to be considered scientific, to be part of actual astronomy, for example, it has to satisfy 3 necessary criteria. And before I go any further, I just want to clarify one little thing. Again, in everyday conversation, the words necessary and sufficient are interchangeable, but in the science context, they are actually quite different. And let me give you an example of that. It is necessary to eat food to survive, but is it sufficient to eat only candy bars and survive? I don't think so. If you were to eat Kit Kats every day as your only source of nutrition, are you going to live? No, because you're not getting vital nutrients, minerals, and vitamins. You're going to die. It's going to take time, but you're going to die. So food is necessary, but Kit Kats are not sufficient as food. So it's a subtlety, but it's one that we kind of have to be a little bit careful about moving forward. So these are 3 things that have to be true. So first off is the hypothesis that you make, can it be proven true? Can it be proven correct? If it cannot be proven correct, it is not scientific. It is something else, and we don't care about it in this class. In a similar sense, I've kind of used this word before, but can your hypothesis be disproved? Can it be proven false? If it cannot be proven false, if it cannot be disproved, it is not scientific. It's something else that we don't care about. And then last but not least is, in order to be able to prove the hypothesis true, in order to prove the hypothesis false, the hypothesis must be testable. Can your hypothesis be tested? If so, how would the test be conducted? How would you do the test, basically? If you can't answer those questions, then we're really not scientific. We're more philosophical in nature. So let's go ahead and kind of look at a case in point, an example. We're going to be looking at something called pseudoscience and science in terms of hypotheses. And the phrase pseudoscience, well, it has a prefix pseudo, which basically means fake or false. So pseudoscience is false science, fake science. Pseudoscience is basically their hypotheses and ideas that sound scientific, but when you peel back the layers, when you really analyze what it's trying to say, it doesn't satisfy those 3 necessary criteria. So we have to be careful of that. And these 2 examples will kind of help us understand those differences. So here are 2 competing hypotheses, number 1 and number 2. So if we go ahead and kind of focus on number 1 to start off with, what we're going to say is that the first hypothesis there, humanity will someday evolve into a higher form of consciousness. What I'm going to claim, my own hypothesis, I know, play on words there, is that this statement, this hypothesis, can't be disproved. On the flip side, the second hypothesis, all tigers have striped skin and striped fur, it can be proved and it can be disproved. All right, so why is this correct? Let's go ahead and focus on the top one. The word that bothers me most in the context of not being able to prove the statement false is the word someday. Someday is an open-ended statement. Does that mean tomorrow? Does that mean next week, next month, next year, next decade, next century, next millennia, next epoch? There's no cutoff day for someday. It's a never-ending journey. Because what you could claim is that if I test your statement and it is proven incorrect, you could say, oh, well, not today, but tomorrow, conduct the test and let's see what happens. And I conduct the test tomorrow and we still haven't evolved. You can go, okay, well, someday means Thursday, Friday, Sunday, Monday, next month, next year, before I die. You can just keep claiming that I have to wait and test again. And because of that, your statement can never be disproved because you can always argue it's just around the corner. Just wait one more day. So that's the first reason that I don't like this statement, that the first statement is more pseudoscience. That sounds scientific, but it can't be proven false. So therefore, it's not a good statement for us to consider in a class like this one. Now, the second statement, what about it? Okay, can this statement be proved? Can this be disproved? Sure. If I find one tiger that does not have striped fur, I have disproved the statement. If I gather tigers by conducting experiments and contacting all of my colleagues around the world, asking them to gather tigers, Tiger King style, then what we can go ahead and say about this one is, if I can't find a single tiger that has non-striped fur and non-striped skin, then the statement is true. It has been proven correct. So the first statement, no good. Second statement might be a little bit kind of weird, but it can be proven true and it can be proven false. It also turns out that the first statement, I have one other problem with it in terms of its non-scientific nature. And that is this idea of higher form of consciousness. When you say a higher form of consciousness, how can I test for a higher form? Does that mean that you have two brains? Does that mean that you can store your consciousness inside your bladder? I mean, what do you mean higher form of consciousness? There's no way to objectively there's no way to objectively test the word higher. That's like trying to objectively test angry, happy, sad. Those are subjective words. They mean different things to different people. Even the word consciousness is tough, but I can go to a medical doctor and I can ask them, what is the current definition of consciousness? He or she could tell me that, and then I can test for it. But the word higher form is more kind of a literary device, not so much a scientific phrase. So therefore, it's also not good for that reason. I can't objectively test a higher form of consciousness because not everyone agrees what is a higher form. But everyone who's a biologist, more specifically a zoologist, they're going to all agree what a tiger is. And I can consult them and they're going to tell me their agreement and then we're good to go. But if I can't get agreement on a higher form of consciousness, then there's no way I can test for it. So that's another problem with the first statement. It sounds interesting. It's actually interesting to kind of debate, maybe in a philosophical kind of sense, but in a scientific sense, this has no merit. We have no reason to debate it at all. It's just outside of our realm because we can't disprove it and we can't objectively test it in any reliable type of way. So what I'd like you to guys go ahead and do is, even though this is an online format, we're going to go ahead and do a pop quiz. Now, before you start having a heart attack or a stroke, this pop quiz, it's not part of your homework, it's not part of your exam. This is kind of merely just an opportunity for you to kind of test your own understanding of the past several slides. Now, ideally, if we were in a classroom setting with other people and not socially distancing and isolating, we would do this in groups of 4, make it kind of a nice, fun, interactive kind of idea. But because this is an online format and this is a recorded lecture, then we're just going to go ahead and do this one solo. So it's just kind of like with playing sports. We're on the honor system. I would like you guys to go ahead and read through the question, pause the video, figure out an answer, and then resume playing the video. But I'm not going to be a referee. I'm not going to kind of be a person who's supervising you in this case. It's just the honor system. But you're going to get more out of this quiz question if you actually kind of try to play by the rules, be a good sportsman, if you will. So here are 3 scientific hypotheses, claims, as they're sometimes called. And we're trying to figure out which of them is a scientific claim. I'm going to give you a hint. One of them is. I'm not going to tell you which one. That's your job. But read through the 3, and then before you resume watching the video, pause it, and then figure out which one it is before continuing on. Be a team player, put it that way. Okay, so assuming that you've read through and you've had a time to think about it, let's go ahead and look at this. Now, admittedly, you might say that the first one has some weird font going on. Well, that's because they have a typo here. They forgot the letter V, and it just says H-A-E. Human beings, hey, never set foot on the moon doesn't make sense. Have makes much more sense. Okay, so human beings have never set foot on the moon. All right, so let's go ahead and kind of look at that one. If we've never set foot on the moon, I'm going to take that literally. That means that we've never put our footprints onto its surface. So that means that if I take my telescope and if I look at the moon and I see no footprints, or if I send a unmanned spacecraft, aka a probe, to the moon and we don't see any footprints, then we have never set foot on the moon. However, if I see footprints on the moon's surface with a telescope or with a man-made probe that I send to the moon, if I even see one set of footprints, even just 1 foot, maybe the person had one leg only, then that statement is incorrect. And how did I test that statement? Well, I used a satellite, aka a probe, or I used a telescope. So I was able to use objective measurements, probes and telescopes, to test the statement to either prove it correct or to prove it incorrect. So it turns out that number 1 is in fact scientific. All right, what about number 2? Some of the laws that govern nature cannot be detected by scientists. Some of the laws. Already I'm kind of suspicious because some is a very open-ended statement. Okay, I don't like it already. But there's another phrase that makes me not like number 2 even more. Cannot be detected. If it cannot be detected, then you cannot test the hypothesis or the law. If you cannot test the law, then it isn't scientific. So for number 2, its lack of testability means that it's not a scientific statement. It's an interesting kind of philosophical statement, but not a scientific one. What about number 3? It is quite possible that in some other galaxy, the laws are fundamentally different than the laws that we are acquainted with. Some other galaxy. Where have we heard a phrase like that one? Someday, humanity will evolve into a higher form of consciousness. Some other galaxy is a never-ending journey, because if I test the Andromeda galaxy and I find that the laws are fundamentally the same, you could say, well, it's in a different galaxy. Try that one. And if I test it and I still disprove it, you can go, oh, it's some other galaxy. Try the one over there. It's one of these never-ending journeys. So for that reason alone, I don't like number 3. It's not scientific because it has no cutoff. I can't objectively disprove the statement because you could always argue, just wait one more time, make one more measurement, and then we're done. So go ahead if you need to, pause the video and go ahead and kind of read through these 3 statements right here. When you're ready, go ahead and resume playing. Now, before I move on, this little gentleman right here, he's making a very kind of introspective statement about the spirit, and I'm using that word in a kind of very, not literal sense, but in a very kind of, I can't think of the word now, metaphorical sense. But there's a part of his statement that I want to focus on real quick. If you conduct a test and it turns out to be negative, then the hypothesis is wrong. To be a scientist, you must gracefully accept the outcome of the test, whether positive or negative. And this is, in my opinion, the hardest part about being a scientist, because think about the last time you were in a fight or in an argument with someone who you cared about, someone who you loved. Do you like being proven wrong to someone who you love? Does it make you feel good inside? Not to me. It makes me feel terrible inside. I'm wrong. And someone who I love has proven me wrong. Someone who I care about, whose opinion matters to me, has proven me wrong. It's just human nature that we don't like to be proven wrong. But as a scientist, we have to just kind of swallow, take a deep breath, and realize, you know what? This is not truth. I cannot keep pushing this forward. It's done. I have to move on. But in my opinion, it's the hardest part about being a scientist. To gracefully accept the outcome of a test, especially when it's wrong, but sometimes when it's right. Okay, so this is the first half of chapter 1. Now we're going to go ahead and focus on the second half of chapter 1. And when it comes out of the second half of chapter 1, the first thing that we're going to be looking at is this idea of units and symbols. And what we're going to say is that most astronomy, and again for the first several chapters, physics variables have units. The reason why is that without units, the variable has no context. So for example, and this is kind of a weird example, but it's the one that kind of pops into my head because of a recent experience that I had. But let's just say that you're walking down the street and a homeless person comes up to you and says, "Excuse me, can I get 5? I'm really hungry." Okay, when he says, "Can I get 5?" what is he actually saying versus what does he mean to say? Well, he meant to say $5, but he said, can you give me 5? So I could have easily given him a high five and that would have satisfied his request. Without the units behind the number makes no sense. If somebody says, I'm going to give you a salary of 10,000 a year, well, do they mean 10,000 lira, 10,000 pesos, 10,000 yen a year? I mean, without the unit behind the number doesn't mean anything. And that's the key difference between science and mathematics. In science, when you get x equals 10, that's the end of the problem. You're done. But in physics, we would say x equals 10 what? The 10 doesn't mean anything until the units give it the proper context. When it comes to units, though, there are two different systems that can be used. The first system is called the CGS system of units. The letters C, G, and S are abbreviations for 3 of the biggest units, most kind of common units in that system. The C is an abbreviation for centimeters, the G is an abbreviation for grams, and the S is an abbreviation for second. Admittedly, most abbreviations, not all of them, but most abbreviations tend to be lowercase, but I've made them uppercase just so they can be dramatic and flashy in this slide. But the CGS system was extremely popular in the late 1700s and the 1800s. Prior to that, there were other competing systems. We don't care about them. But in the 1800s, the CGS system was king. Even in the early 1900s, the CGS system kind of limped along for quite some time. But it turns out that the MKS system, which kind of came about in the early 1900s and became very popular in the kind of mid-1900s, this is a system that is still used today. And in fact, 99% of the world, except for the US and one other country that I can't think about who's very, very small and tiny, 99% of the world uses the MKS system for the most part. You know, they might have their own homegrown units they add in just for fun, but they use the MKS system for the most part. Us Americans, we're very, very odd. We use something called the British system. Now, why is that? Well, what country did America come from prior to 1776? Well, we came from Britain. And at that time, they used the British system, which was kind of like a modification of the CGS system. So sadly, America, we still use a system that really was abandoned in the 1800s, mid-1800s, but still, we use that system today. So it's kind of sad as a scientist to hear it. But we want to focus on the MKS system, where M is an abbreviation for meters, K is an abbreviation for kilograms, but there's a subtlety. We'll have to watch out for that in chapter 4. And then S is the abbreviation for seconds in this case. And first things first, this idea of meters. Well, again, most of us who are listening to this presentation are quote unquote red-blooded Americans. Yeah, good luck Google Translate on the spelling of that one. But still, we don't use meters for distance. We use things like feet, yards, inches, miles. But those are not CGS and those are definitely not MKS units. To understand meters, because you will have to get some sort of understanding about them for the first several chapters of the semester and also on and off throughout the rest of the chapter. For an average person, and that's a very loaded statement, but for an average person, 1 meter is the distance from the bottom of your foot to your hip joint. That's roughly 1 meter. Again, it does depend upon ethnicity and gender and age, but you know, for us in this classroom setting, more or less people in their late teens, early 20s, 1 meter is roughly that distance that I've given to you. So that's kind of how I think about it in my head. And this is kind of a gross, kind of off color, dare I say, blue analogy. But if I'm thinking about a distance of 10 meters, then I basically kind of imagine 10 sawed off legs, kind of serial killer style, placed end to end to end, and that's 10 meters. So that helps me personally, in my weird twisted sense of mind, to understand 15 meters, 70 meters, 3 meters. It's just a bunch of legs glued end to end to end. If you have a better system, a better way of remembering meters, please use that, that's fine. But my system is one that you'll probably never forget because it's so weird and off color to begin with. But anyways, I digress. It turns out that other variables are hybrids, dare I say, combinations of these three fundamental units. So for example, there's a variable that we'll talk more about in a future chapter called velocity or speed. It has units, part of the MKS system, that are called meters per second. So meters and seconds as part of a fraction. There's another variable that we'll talk about in a future chapter as well called force. It's a very complicated variable, and it has very complicated units behind it. Turns out that the units of force are kilogram meter per second squared. So it has both kilogram, meters, and seconds all together in a very complicated fraction to illustrate the units for this very complicated variable called force as well. Now, when you want to deal with multiple variables like velocity and force and energy and time and height and distance and density and length and so on and so on and so on, it turns out that all those variables and the units that describe them, they become part of a very large system of units called the Système International des Units, or as we abbreviate them here in the kind of Western part of the world, the SI system. The nice thing about the SI system is that these units are easily combined with what are called metric prefixes. And I guarantee that you've heard metric prefixes before, you just might not be aware of them in an everyday context. So here are some of the more common metric prefixes. There are more of them out there, but these are the ones that we're going to see throughout the semester quite often. So here's the abbreviation, the symbol. Here's the actual kind of prefix to the unit that it attaches to. And here is kind of its translation for the size or the scope of the metric prefix. So for example, if you are big into health, then maybe you know how many milligrams of vitamin E you have to eat every day. Okay, well, gram is the unit, but the prefix milli is the metric prefix behind it. So it just means 1,000th of a gram. In a similar sense, when you download a typical PDF file from a website, it might be something like 300 kilobytes. Okay, byte is the unit, kilo is the metric prefix that says that it's basically 205,000 bytes of information. If you're a fan of classic movies, specifically Back to the Future, how much energy did the DeLorean require to activate the flux capacitor? 1.21 gigawatts. Okay, giga is the prefix, watt is the variable itself, but giga just means billion. So each of these prefixes and the symbol or the abbreviation behind it are important to recognize because something like nano has the translation of billionth, th at the end. It's a very, very small quantity, whereas something with giga as a prefix is billion, no th, means very, very large in comparison. So with metric prefixes associated with the SI system, because admittedly, for example, when was the last time someone told you that they had to walk 5 megamiles, 5 giga inches? Just doesn't, it sounds awkward. There's technically nothing wrong with it, but no one in their right mind is going to use it that way. But even with these metric prefixes and these kind of SI systems, it turns out that astronomy, despite what you might think, we deal with the very large, okay, makes sense, but we also deal with very small phenomenon as well, aka very small numbers as well. So case in point, the distance between the Earth and the Sun is a very large number. The mass, which we don't know what that variable means yet, but the mass of a hydrogen atom is a good example of a small number. So here are the two numbers for these two variables, distance and mass. So the distance between the Earth and the Sun, 149,600,000,000 meters. That's a big number. Will metric prefixes help out? Sure. So if I wanted to use a metric prefix, then the distance between the Earth and the Sun is 149.6 gigameters, because again, giga means billion, So if I multiply 149.6 times 1 billion, I get 149,600,000,000 meters. Okay, so metric prefixes help, but it turns out that the mass of the hydrogen atom, look how many zeros are to the right of that decimal place before we get to the first non-zero digit, the 1 in this case. It's a lot of zeros. And we're already using metric prefixes in this unit for mass. So using a different metric prefix isn't going to help that much. So metric prefixes can help, but there are limitations. So what we can do is that when we have very large numbers or when we have very small numbers, it's often a smart idea to represent those numbers using powers of 10 notation, as our book calls it, or as pretty much every other book calls it, using scientific notation. So let's go ahead and look at this scientific or powers of 10 notation. What you're basically doing is you're basically using a factor tree to rewrite the number in a much easier to recognize format. So how does that work? Well, if I were to use a factor tree on that very large number, it would look something like this. It's gross because there's so many tens that I could factor out in my factor tree over and over and over again. But what I want you to notice is that in our powers of 10 notation, because I'm factoring out by 10, I want you to notice that I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 powers of 10 that I factored out. And by using this scientific notation, by using this powers of 10 notation, I can rewrite that number in this fashion. 1.496 times 10 to the 11th power meters. But the key thing here is that I have a base of 10, an exponent of positive 11, and then a leading value of 1.496. All right. So the base of 10 is kind of where the powers of 10 notation comes from, but it's really the exponent that is very important for us in this class. Case in point, if you do the same thing for the mass of the hydrogen atom, you actually create the factor tree not with powers of 10, but with powers of 1/10, aka th, at the end. When you do that, you get this different number, 1.67 times 10 to the negative 27th power. And so this is still written in powers of 10 notation because we still have a leading value, we still have a base of 10. It's just now that our exponent is a negative number. And this is crucial because in astronomy, if you see a number written in scientific notation, written in powers of 10 notation, you have to immediately recognize, is the number big or is the number small? Look at the exponent. If the exponent is positive, you're talking a huge number. If the exponent is negative, you're talking about a tiny number in comparison. So you're going to see scientific notation pop up very often throughout the semester. Will you have to do math problems with powers of 10 notation? Not for this class. Maybe for Astronomy 25, but not for this class. But will you have to recognize the scale of those numbers? Absolutely. Now, there's a third part to chapter 1, and this is kind of like a quick tour of astronomy, very, very fast, kind of like a 5-minute tour of the Smithsonian. You're not going to get a lot from it, but hey, it's better than nothing. So we need to understand our perspective. So let's kind of think about this idea of where we are in the universe. So where are you right now? Hopefully in your house. Okay, your house is one house of many on your block. Your block is one block of many in your city. Your city is one city of many in the county. Your county is one county of many in the state of the United States. Your state is one state of many in the United States. The United States is one country of many in the world. So I can keep zooming out and zooming out and zooming out to understand your scale of where you are, your kind of perspective of where you are. So we can't appreciate astronomy. We can't really grasp onto it until we understand where we fit into astronomy. And these two pictures right here, they just kind of represent good old-fashioned Earth from two different satellites, one with color, one without color. But the key idea here is that we're going to say that we live on planet Earth. But what we're going to say about that, though, is that kind of like when I took you from your house and slowly zoomed out to the Earth, we can keep zooming out. The Earth is one planet of many. It is part of a solar system of planets. There is a sun, and there are 8 planets, of which we are one of those 8 planets in our solar system. So for example, in this artist depiction of kind of a side profile shot of our solar system, this red arrow that I've added here is the distance from the sun to the first planet that we're going to call Mercury. Its distance is 0.38 AU. Okay, well, what is an AU? All right, well, an AU, it corresponds to a very specific number. So let me go ahead and kind of fast forward to that real quickly. You'll notice that this distance here for the sun is 1 AU. Okay, well, we know from a previous slide that the distance between the Earth and the sun is 149,600,000,000 meters. Well, in astronomy, we use the SI system, but we have a few other units that are kind of legacy units from our past. And the AU unit is one of those legacies. AU is an abbreviation for astronomical unit. 1 AU is equal to 149,600,000,000 meters. That's a lot of legs that I would have to saw off serial killer style to cover that distance. In fact, that would cover pretty much the entire population of the Earth, plus some cemeteries that I would have to loot, to be honest. So that's a lot of legs, that's a lot of meters, to be honest. So with that kind of being said, if we look at Mercury, it's a little bit less than half of that distance. It's 0.38 AU, which is less than 0.5. So it's kind of less than half of 149 billion. So it's less than half of 75 billion meters. Still a long distance by human standards. But the nice thing about using this AU unit is that even though it's not SI, I'm taking a very kind of large distance and I'm representing it as a much smaller number. In this case, 0.38 in this case. Venus has a similar issue. It's about 3/4 of an AU, not quite 7.5, but it's 7.2. But still, it's about 75% of 149,600,000,000 meters, which if I do that multiplication is still a pretty big number. So I'd rather just rewrite that as 0.72 AU. It just makes me feel better, makes it easier to read in the first place. If I kind of keep going further out to Mars, it's about 1.5 times Earth to Sun distance. I can keep going further and further and further and further and further until I get to the last planet in our solar system, which is an insanely large distance away from the sun, 30 AU. And already we're starting to get to big numbers again, 30. But again, 1 AU just kind of corresponds to 149,600,000,000 meters. So this symbol right here means is defined to be. This means is equivalent to. So for example, brother is defined to be a person related to you by birth or by adoption, having the same parents. The word bro is equivalent to brother. So this is kind of like bro, this is brother, and this is a person related to you by common DNA or adoption with the same parents. So this is kind of a definition relationship, and this is an equivalent statement, a similar statement, the abbreviation, if you will. All right, well, we've zoomed out to our solar system. We can keep zooming out. Our solar system is one solar system of billions in the Milky Way galaxy. Now, how big is the Milky Way galaxy? It is huge. If I wanted to use SI units, the number would be a very large powers of 10 number, and there's nothing wrong with that. But again, for astronomy, we like to introduce our own units to make the number smaller and easier to digest. So case in point, there is a unit called a light year, and its abbreviation is LY, kind of like you see in the golden color. 1 light year in astronomy is defined to be 9.46 times 10 to the 15 meters. So we're already in very large numbers. How large is that? Basically 946,000 gigameters, which is already huge. It's also equivalent to 63,000 and change extra AU. So it's a huge number. But it turns out that if you use light years as a unit of distance, and that seems kind of weird because the word year, when you use it in everyday conversation, has a unit of time. But a light year is basically the distance that a laser beam of light would travel if it could travel uninterrupted for 1 year, aka it's a huge distance. But it turns out that our Milky Way galaxy, of which we are a part of, its diameter is 100,000 light years. So if I wanted to kind of put that into AU distances, 100,000, that would be 6,300,000 AU. That's a huge number. You could put it in scientific notation, that's okay, but it still has to be in scientific notation. If I use light years, 100,000, it's not great, but it is a relatively small, easy number to digest. And it turns out that there's another unit called parsec, abbreviated PC, which is even more friendly. It turns out that in astronomy, 1 parsec is 3.26 light years. And of course, what movie made the parsec unit famous? Star Wars, A New Hope. The Kessel Run? Yeah, I know. It makes it seem like a unit of time, but thanks to the kind of Han Solo movie, we now understand that it actually was distance in a very clever roundabout fashion. But nonetheless, our Milky Way galaxy, about 100,000 light years, roughly about 33,000, give or take, parsecs, which again is a much smaller number to write and therefore much more friendly to read because we all know 33,000. It's a big number, but it's manageable. But again, scientific notation can be tough. So therefore, introducing our own units in addition to SI becomes very kind of nice and friendly. But again, just like life, it gets worse. I can keep zooming out because we have many galaxies, not just our own, in the universe. Our galaxy, the Milky Way, is one of many galaxies in this structure that we call the local group of galaxies, or just the local group. Now this picture is a little confusing because it's giving us both 2-dimensional and 3-dimensional representations of the local group of galaxies. This side shot where all the colors are at different heights relative to each other, this is 3-dimensional. These little kind of lines and the dots kind of represent where they are in a 2-dimensional, kind of flattened perspective, kind of how clustered they are to their neighbors. So the Milky Way is right here, and there are lots of other galaxies in this structure. So the biggest one that we're going to talk about most often is this one right here, the Andromeda Galaxy, sometimes called M31 for historical reasons. But there's lots of other ones as well, like you might have heard about, for example, the Large Magellanic Cloud. You might have heard about the, where'd it run off to? The M33, the Triangulum Galaxy. But it turns out that these galaxies, in terms of how far apart they are kind of horizontally from each other, is best kind of understood by this disk right here and this outer disk right here. This light colored disk corresponds to 1 million light years. So for example, if you look at the Milky Way galaxy right here and the Pegasus galaxy, we're roughly about 100 million light years away from the Pegasus galaxy. It's a long distance. So again, we're back up to huge numbers, 1 million. I could use powers of 10, that's okay, but it's still powers of 10. It's still kind of rough to look at the first time. But it turns out that it gets even worse. Our local group is one group of many in something that we're going to call a supercluster. And it turns out that there's a weird subtlety that I have to mention in this slide. So you'll notice here that the local group is this dot in a computer simulation. We are close to this other thing called the Virgo supercluster, but it turns out that in recent years, within the past 10 years, past 15 years, it has been determined that we are definitely part of the Virgo supercluster. To put it in terms of human anatomy, we're kind of like the appendix of the Virgo intestine. We're part of it, but we're kind of like an offshoot, kind of like how your appendix is an offshoot of your intestines. But within the past 5 to 8 years, there has been a change. It turns out that prior to about 8 to 10 years ago, the Hydra supercluster, the Centaurus supercluster, the Virgo supercluster, we assumed that they were all separate, distinguishable from each other. But it turns out within the past 5 to 8 years, there's growing evidence that we are all one giant supercluster. And because of that, in newer textbooks, starting in a couple of years, the local group is not going to be called part of the Virgo supercluster. We are going to be called part of something called the Laniakea supercluster. Now that's a Hawaiian word because the evidence for this theory came from telescopes in Hawaii. So it makes sense there. So in our textbook, it states that our local group that we are just one small element of is part of the Virgo supercluster. And that's not the best way to describe it. Our book says it's correct, and a lot of books right now say it's correct. But in the coming years, I say at least 5, maybe even 3 if we get lucky, it's going to be renamed, and it's going to be universally accepted as the Laniakea supercluster. Virgo, Hydra, and Centaurus are just going to be small sections of the Laniakea supercluster, kind of like how Orange County is one county of many in the state of California. Same idea. But it turns out that there are other superclusters in our immediate vicinity. Now, I'm using the word immediate vicinity in a very kind of joking context because the kind of girth, the kind of width of all of these different superclusters is 100 megaparsecs. So I'm using a metric prefix, M, for mega, million. And I'm using parsecs because that's the best that we have in astronomy. But it's still a pretty big number, 100 megaparsecs. But these local superclusters, the Laniakea, the Perseus, the Pegasus, and all the other ones that we see right here, there are many superclusters that exist in the universe. And it turns out that if you take higher levels of astronomy, there are other vocabulary terms that you can learn about that go beyond superclusters. We're not going to care about them. What we're going to say is that if you zoom out one more time, then we're going to say that the Laniakea supercluster is part of the universe. Okay, well, what is the universe? Quite simply, the universe is the summation, or better said, the totality of everything in space. So the Earth is part of the universe. The Milky Way galaxy is part of the universe. The Laniakea supercluster is a part of the universe. This picture that I'm showing you here isn't the totality of everything in space because this is from a telescope only looking in one direction. But what I want you to notice is that this is a very special picture called the Hubble Ultra Deep Field because it came from the Hubble Space Telescope. And basically what it was is it's a very detailed picture showing you how many galaxies are visible in a tiny, tiny, tiny section of the nighttime sky, roughly about the width of your thumb when you hold it far away from your head and close one eye. That's a tiny patch of the sky that we're looking at. So there are countless numbers of galaxies that are just in what we see in the nighttime sky. And we're only looking at the northern part. We can't see the southern part because the pesky Earth gets in the way. But each one of these are galaxies which contain billions of solar systems and therefore trillions of planets. Maybe they have life, maybe they don't. That's more of a philosophical debate. But just the amount of raw material, the amount of stuff in the universe is sometimes incomprehensible. The best analogy that I can give you is trying to count the number of grains of sand in all of the beaches on Earth. It's going to be a high number. And that's kind of what we're looking at right here. So with this kind of cosmic perspective taken into account, we'll go ahead and kind of wrap up this chapter, and then we'll go ahead and kind of get ready for our next chapter shortly. Thank you for listening, and take care out there.